Hello, everyone, and welcome to this free webinar presented by WePast. My name is Christina Ruiz, and I will be your moderator today. Throughout the webinar, we will stop the presentation to review. There will be several multiple-choice review questions which you will be able to answer in the polls section. Please go ahead and respond to these questions as they come up. You will have about a minute to answer each one. During the webinar, please feel free to use the chat to ask questions and discuss the topic. We will take time after the presentation to answer these. This and other recorded webinars will be available to WePast subscribers. You can register through wepast.com to become a subscriber. Today's topic is Radiation Protection and Quality Assurance for Therapy Certification Board Review, presented by Frank Ascoli, Medical Radiation Physicist at US Oncology in Providence, Rhode Island. Thank you for joining us, Frank.
Thank you, Christina. Again, welcome everyone to this webinar. This is a half of a two-part board review for radiation therapy certification. Second part will be delivered tomorrow evening at the same time, 6 p.m. Eastern. This is meant as a review, so there'll be a lot of questions that I will be throwing out there as the talk progresses. It's a review of all of the important items that a therapist should know in order to successfully get through the registry exam. It's going to be many topics that we cover, and the first is sources of radiation. And let's start off with a question. Which federal agency has responsibility for reactor-produced isotopes? So remember, reactor-produced isotopes, these are stable elements that are put into a nuclear reactor and made radioactive. And these are not the webinar questions that you will be asked to answer. Those are separate questions. These are just questions in the context of the talk that I'm giving, just to get you thinking about all of the different items of radiation safety, protection, radiation physics that you need for passing the registry exam. And the answer to this question is the Nuclear Regulatory Commission, the NRC, regulates anything that is produced in a radiation nuclear reactor. Does the NRC license radium? Now remember, radium is a natural occurring isotope. It is dug up out of the earth and it is mined. And does the Nuclear Regulatory Commission have jurisdiction over radium? And the answer is no. And of course, who does have jurisdiction over radium? The states. The individual states control anything that is called naturally occurring radioactive material, or NARM, N-A-R-M, naturally occurring radioactive material. The states have control over that, and the states actually have control over any of the so-called man-made sources of radiation. These are sources that are electrically produced, such as X-ray machines and linear accelerators. So the Nuclear Regulatory Commission, surprisingly, has a very narrow focus and a very narrow scope, only reactor-produced isotopes. That means that they licensed cobalt-60, which is hardly ever used anymore, and they don't license linear accelerators, which are always used. That falls to the purview of the individual states. I'm going to show you an example. I'm going to show you many examples of different uses of radioisotopes in medicine. And the idea behind this is to learn what the isotope is and some of the important factors, technical factors concerning that isotope. In this first example, we see a technique called an accelerated partial breast irradiation, APBI, and it's in the patient's left breast, and it's the placement of a balloon catheter, which you can see on the picture on the right. The balloon catheter is high up in the breast, and you can see a central channel to the catheter where an isotope would be loaded to treat the lumpectomy cavity. This is an example of where we would use iridium-192 with a 73-day half-life, 468 keV. This is an example of high dose rate HDR radiation. HDR radiation is used primarily for this type of accelerated partial breast irradiation, and it is also used extensively in gynecological applications. Here's an example of a gynecological application. This is a vaginal cylinder. The vaginal cylinder is placed into the woman's vagina, and it's usually following hysterectomy, so there is a partial vagina. It irradiates the upper third of the vaginal mucosa, and this is given in an attempt to eradicate any cancer cells that may be left behind after the hysterectomy. Very common treatment. A lot of women get this as a boost to external beam radiation. The isotope that's used here is, again, iridium-192 with a 73-day half-life. And on this drawing, I will also point out this is a computerized treatment plan, and in color are the organs of risk that should be avoided by the radiation. And this type of treatment does a very, very nice job of irradiating the vaginal mucosa and minimizing dose to the outlined organs that you see there. In mauve, you see small bowel, which we try to avoid as much as possible. Urinary bladder, which sometimes sits very close to the application, and colon, which is also very close to the application. Rectum also. So the HDR delivers a very high local dose. This is an example of an iodine-125 prostate seed implant. The isotope is, of course, iodine-125 with a 60-day half-life and 27 keV. It's a very, very low energy isotope. The isotope has an energy very similar to mammography, the lowest exam that's done in an X-ray department. 27 keV means that the radiation stays very, very concentrated where it's implanted into the prostate gland. And it's done through a transperineal approach. Many of you are familiar with this. That white grid is placed against the patient's perineum. Individual needles containing the isotope are loaded into those needles, injected through the skin into the prostate with ultrasound guidance. The ultrasound apparatus is below the white template. You see it covered in plastic. And the ultrasound is transrectal, giving the doctor an excellent view of the prostate while the needles are going in, and the doctor drops the seeds, the radioactive seeds, directly into the prostate gland. Another isotope that is used commonly, palladium-103, 17-day half-life, 21 keV, and we've also seen recently the use of cesium-131 with a 9.7-day half-life and an energy of 30 keV. The advantage of cesium-131 is it has almost the same energy as iodine, but a much shorter half-life. So the doctors can then deliver that radiation in a very, very short period of time. We see this used as a boost to external beam radiation. We also see it used for patients that have higher Gleason scores, where the radiation needs to be given in a much shorter fractionation as opposed to the 60 days of the iodine-125. This is the cobalt machine that I alluded to earlier. The Nuclear Regulatory Commission licenses cobalt. Cobalt-60 has a 5-year half-life and an average energy of 1.25 MeV. It was really the first megavoltage machine in use. Even though there wasn't any voltage, this is the energy of the gamma rays coming from the cobalt-60 source. 5-year half-life meant that the source would be changed every 5 years. It was a very high activity source, usually 10,000 curies. It has definitely fallen out of favor in this country for a number of reasons. The linear accelerators have far less penumbra, much sharper beam, but there was so much licensing involved with cobalt-60 in the last decade that people are moving away from cobalt-60 and all of the problems that it presents from a licensing standpoint. But it may still find use in some of the clinics. It is absolutely accepted in other countries throughout the world where resources are not available to support a linear accelerator. These cobalt units are very robust. They hardly break down. There's very, very little mechanical to them. That rod sticking out of the head of the machine is a rod that we use if the source ever gets stuck. This rod has a color code on it. If it's showing red, it means that the source is out in the deployed position. If it's showing yellow, it's somewhat safe. If it shows blue, that means the source is pushed back all the way into the lead housing and it is safe to enter the room. The sources hardly ever get stuck, but if there was a power failure during the evening, sometimes the source would find its way out into the on position due to springs vibrating, whatever. And the external monitor in the room would start screaming. The therapist would call the physicist. The physicist would say, "Don't go in the room, shut the door, I'll be right there." The physicist grabs the rod, boom, pushes the source back into position, and hopefully doesn't get much dose in the process. But this is how it was done. Luckily, we don't see too much of this anymore today. This is a set of gynecological applicators called Fletcher suit applicators, and they are used for cesium-137. Cesium-137 is an alternative to radium. It's a 30-year half-life, very relatively high energy. Of course, radium-226, 1,625-year half-life, very high energy due to the decay of radon. Radium is no longer used. It had too high an energy, really, for brachytherapy applications. But the other problem with radium is that these sources, over time, these were sealed sources, and over time they would develop helium gas within the source itself, because radium is an alpha emitter. It decays to radon-222, gives off an alpha particle, which is 2 protons, 2 neutrons. Helium is produced within the encapsulation. They become under pressure, and any little trauma could bust that capsule, and you would have a radium contamination issue at hand. And radium has definitely fallen out of favor. If there is going to be an implant with low dose rate LDR radiation, cesium-137 is the preferred isotope that we use today. But that has been really been subsumed by HDR. And there still are places using cesium-137 for low dose rate, but most of the brachytherapy today is done with HDR. Here's some radioactive seeds, not iodine. These are radon-222 seeds, really no longer used, very, very rare, short half-life and very high energy. Gold-198 had a better energy, 2.7-day half-life, and there are still some applications for gold-198 in interstitial permanent brachytherapy implants. HDR has a lot of use today. These are usually 12th Curie sources, and they give off a whopping dose rate of 493 gray per hour at 1 centimeter. It takes about 2 feet of concrete to shield this, and there are extensive QA and safety procedures. The NRC does license iridium because iridium is reactor produced. So the Nuclear Regulatory Commission is involved in the licensure of iridium-192. This is important. The worker exposure level, not ever to exceed 2 milligram in an hour. So no matter what we do as radiation workers in the field of radiation oncology, never ever are we to be exposed to more than 2 milligram per hour. That is a hard, fast rule from the Nuclear Regulatory Commission, and all of the shielding design, everything that is done to protect the public from these sources of radiation and the workers from the sources of radiation has to come in under 2 milligram per hour in order for it to be properly licensed. So another question, what would you do if an HDR source fails to retract? And of course, the answer is you need to have a safety container nearby. This is part of the delivery system. You always have a safety container nearby. And if the source failed to retract, the doctor, the physicist rush into the room, take the applicator out, drop it into the source container if all else fails. By that I mean if the emergency stops don't work, if the emergency alarm is still going off and you've tried to retract the source manually and all else fails, there is a safety container in the room for the containment of the applicator. So here is our first webinar question. And the question is, which of these isotopes has the shortest half-life? And I'm going to show you some choices here, and you ought to pick the right one. Cobalt-60, Palladium-103, iodine 125, excuse me, and iridium 192. So which of those has the shortest half-life? I'll give you a moment to answer.
Great. So for those of you who are just joining us now or aren't familiar, you can go ahead and answer the poll questions. They should be posted on the left-hand side of the window. And once everyone has had a chance to submit their answers, you'll be able to see how others have responded, and we'll review the answer in about a minute. All right, looks like some answers are already coming in. Okay, great. Frank, I think we can go over the answer.
Okay, the answer for the shortest half-life is palladium 103. The answer is B. Okay, I'm going to continue with the talk. What are the principal methods, the principal decay mechanisms? So here are the big five, and it's actually the first three that are the most important ones. Alpha decay. A isotope can decay by emitting a huge alpha particle, 2 protons and 2 neutrons, very, very quickly getting rid of mass to stabilize into a lighter, a smaller isotope. Beta plus is called positron decay. Beta minus is called negatron decay. Most of the isotopes that we use in medicine are beta minus negatron decay isotopes. Electron capture and isomeric transition are mechanisms that we don't hear much about in medicine. They are mostly used in nuclear medicine. I meant that we don't hear much about in radiation medicine. They're mostly important to nuclear medicine, but they also serve to cause the decay of the isotope into a stable isotope. And in doing that, it gives off gamma radiation. So these are the five principal means of radioactive decay that we come across in the field of radiation. Here is the second Webex question. Low activity radioactive sources such as iodine 125 may be disposed of after how many half-lives? Now, you will see that some of these questions I don't really go over ahead of time, but this is a board review, and it's a good chance to test your knowledge to see if you can actually come up with the answer before I even address it. So, low activity radioactive sources, such as iodine 125, after how many half-lives can you get rid of them? And here are your choices. After 1 half-life, after 5 half-lives, after 10 half-lives, or never.
Okay, thanks, Frank. It looks like our participants are getting the hang of it, and they've already weighed in. So why don't we go ahead and go over the answer?
Okay, the answer is 10 half-lives. You have up to 10 half-lives. You should wait before you can dispose of iodine 125. Now, by disposal, it really means you can actually just get rid of them in the trash, because at that point, they are down to background levels. But we don't usually recommend that. People get nervous when they find these pellets in trash. And the best thing to do is really just send them back to the vendor and let the vendor dispose of them. But they don't have to be sent under a radioactive label. Machine-produced radiation is caused by the bombardment of tungsten. And the process is called Bremsstrahlung radiation. A high-energy electron slams into a piece of tungsten and emits forward-directed photon radiation. This is the Bremsstrahlung process, which is prevalent, which is predominant, which is how we produce linear accelerator-based radiation that we treat our patients with. Some of the other machines that are used to cause X-ray production or proton or particle production. These are some of the other machines used in the field of radiation medicine. And there is the ultra-voltage machine, which many of you may not have had a chance to work with. It is used for skin cancer in lower kV ranges. Ultra-voltage is really between 200 and 300 kV. Superficial voltage is used from about 50 to 100 kV. There is a lot of use of superficial X-ray machine for the treatment of skin cancer, we see a little use of orthovoltage, which has slightly better penetration. Cyclotron, there's about 20 in the country that are currently operating, another 20 on the books. This is strictly for proton beam therapy, and of course, linear accelerators are the workhorse of radiation departments. There are about 3,000 radiation departments throughout the country, and most of them are using linear accelerators, if not all of them. And the research academic centers, if they're fortunate enough and have the funds enough, can build a cyclotron facility. Linear accelerators operate in the range from 4 to 25 MV, although today the practice is really from about 6 MV to 10 MV and an occasional 15 MV, and maybe some 18 MV. With good treatment planning, the use of higher energies not indicated, and in fact, with intensity modulated radiotherapy, the use of very high energy is avoided, and most of the work done today in radiation therapy is between 6 and 10 MV. Here's a picture of an orthovoltage machine. Obviously goes back quite a ways. This is probably a Siemens machine, and that's what they look like. And look at the large cone that was actually placed in contact to the patient. The X-ray tube was enormous because it had to support 200 to 300,000 volts. So what do you accelerate in a cyclotron? Protons. What kind of drugs can you make with a cyclotron? PET drugs, PET proton rich, decay by positron emission. Or electron capture. What happens? What do they release? When these proton-rich positron emitters interact, they release two opposed 0.511 MeV photons, which are used in coincidence counting circuitry in a PET, positron emission tomography unit. Radiation, of course, is a type of electromagnetic radiation, and it behaves as both a particle and a wave. I like to show it this way. It's bundles of packaged energy. That means that the energy has a frequency. The frequency is what gives it an electromagnetic energy component, but it also behaves as particles. So think of it as packages, packets of energy. That's the definition of quanta, packets of energy. The basic equation describing that energy is Planck's equation, E equals Planck's constant times the frequency, or E is equal to, Planck's constant times the speed of light divided by the wavelength. And if you multiply the Planck's constant, which is a constant, times the speed of light, which is a constant, you end up with 12.4, and that's a lot of times how the equation is shown. E is equal to 12.4 divided by the wavelength. How does energy vary with wavelength? Inversely, the shorter the wavelength, the higher the energy. Since wavelength is in the denominator, as the denominator gets smaller, 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 the energy goes up, 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 up. So higher energy is associated with shorter wavelengths. Here are some questions on attenuation. After 5 half-value layers, the remaining fraction is half of a half of a half of a half, etc. And if you do the math, and that's the way you should handle these problems, these half-value layer problems are best handled by just taking half of a half of a half of a half. You end up with 1/32. Linear attenuation coefficient, however, is different from half-value layer. It has a value of per centimeter, and if you put the equation in use that you learned while you studied linear attenuation coefficient and half-value layer, if the linear attenuation coefficient of the beam is 0.1 per centimeter, the half-value layer is 6.93. So the equation is that linear attenuation equals 0.693 divided by the half-value layer. Vice versa, the half-value layer is equal to 0.693 divided by the linear attenuation coefficient. That was a simple equation you learned when you studied radiation physics. What is quality? Quality is actually measuring the half-value layer. The half-value layer is a measure of the quality or the energy of the beam. An X-ray beam is polychromatic. By increasing the filter thickness, the half-value layer does what and the intensity does what. If you increase the filter thickness, the half-value layer goes up, the intensity goes down. Inverse square law is described as a mathematical concept. A lot of people think it's a physical, has to do with physics. It's a physical phenomena where the radiation falls off as the square of the distance. This is not the case. I mean, it does definitely fall off as the square of the distance, but it has nothing to do with physics. It has everything to do with mathematics. As you can see from this example, if you start off at a distance of 1D, you have this little square of radiation. If you go to 2D, because of divergence, that one square becomes 4 squares. If you go to 3D, that one square becomes 9 squares. So it is an inverse square relationship, 1 over the distance squared. It's purely mathematics, from a point source to spreading the radiation out over a larger and larger area, because the area of a circle varies as the square of the radius. We have the inverse square law. Okay, so here's a question on inverse square law. Certainly your best friend when it comes to radiation protection. If you move from 1 to 4 feet away, how much does your exposure go down by? So this is a Webex question. Go ahead, Christina.
All right, for those of you who are just joining us, we have the poll option not in the chat, but there's a separate polls tab that you can go to, and then you can answer this question live, and you'll be able to see how other participants are answering. All right, great. Looks like folks are letting the questions come in, so their answers are coming in. So why don't we go ahead and go over the answer, Frank?
Okay. Let's leave it for a minute here. Okay, wait a minute, hold on. Okay, here we go. Sorry about that, folks. My mouse was in the wrong place. The answer is 16 times, 4 times. Oh, that's what I want to stop right there. Is it either 16 times or 4 times? The answer is 16 times. Here's another webinar question, another Webex question. Out of these terms which are used in treatment planning, only one of these terms that you studied in treatment planning, PDD, percent depth dose, TAR, tissue to air ratio, TPR, tissue phantom ratio, TMR, tissue maximum ratio, only one of those has the inverse square law included in it. Which one is it? So go ahead and give your answers.
So this question is also available in the polls. So just go on over from, if you're in the chat room, over to polls, and you'll be able to see this question live.
So you can choose A, B, C, or D.
All right, great. I think we can go over the answer, Frank.
Mm-hmm. And the answer is PDD. PDD, percent depth dose, is the only one which has the inverse square law. And this is why, if you compare percent depth dose to tissue maximum ratio, for example, for an SSD treatment versus an SAD treatment, if you compare the two, the percent depth dose will always have a smaller value because it includes the inverse square law in it. So for the same depth in the patient, the percent depth dose will always be the smaller number. We're going to go over X-ray interactions with matter, and we'll talk about electron interactions and also other particles. So the next part of this talk is having to do with interactions with material. The first thing I want to go over is something called the quality factor. And here's a question: what is the quality factor for X-ray and gamma ray? And the answer is 1. The QF for X-ray and gamma ray, conveniently for us in radiation oncology and in diagnostic radiology, for the energies that we use and the type of radiation that we use, the quality factor is always 1. What is it for electrons? Again, the quality factor is 1 for electrons. What is it for neutrons? Say 10. There's a range depending upon the neutron energy. Quality factor for neutrons is taken to be about 10. For protons, it's taken to be 2. And for very heavy particles, the quality factor can be up to 20. Now remember, you take the quality factor and you multiply it by the centigrade dose to get the REM dose or the sievert dose. So quality factor times centigrade equals REMS. Quality factor times gray, I should say, equals REMS. So REM, the term REM, R-E-M, REM includes the quality factor. The centigrade does not. Fortunately for the radiation that we use, for the most part, linear accelerator based radiation and electrons, quality factor is 1, and a gray equals a REM. The key interaction where energy is given to the patient is the photon ionizing the material that it bombards. So the photon ionizes the atom, a target atom, and that atom could be anything within the patient. Anything within the patient. That target atom could be an atom of oxygen, of hydrogen, of nitrogen. It could be an atom of carbon. The radiation causes the ionization of an atom emitting an electron, and in that basic interaction, kinetic energy is released. Radiation enters, frees an electron, the electron is released with kinetic energy. So from the beam of radiation, kinetic energy is extracted, and that's how we get dose to the patient. Dose to the patient is measured in terms of the number of ionizations produced within the patient. That is dose to the patient. It is called KERMA, kinetic energy released in matter, KERMA, and it has the units of joules per kilogram, which is exactly the unit for the gray or the rad. So this is what we do. We cause ionizations within the patient. We release electrons. The electrons carry kinetic energy that has been extracted from the beam of radiation. Of course, the beam of radiation has a lot more energy than is required to produce just 1 ion pair. It goes on to produce hundreds and thousands of ion pairs. So in the end, all of that energy is emitted, is released, is given up by ionization. That's how we get dose to the patient. Some of the interactions that occur are listed in the next slides. There's coherent interaction, which shows a photon coming in, interacts with an electron, but does not cause the release of that electron. Rather, the energy causes the electron to vibrate while captive in its orbit, releasing a similar photon of similar energy. So no energy is imparted, no dose to the patient. Photoelectric effect, very important in the world of diagnostic X-ray. Binding energy is broken. There is no scattered radiation. This is the key point with photoelectric effects. If photoelectric effects do not result in scattered radiation, the diagnostic radiology people love this because scatter produces fog and haze and gray and lack of contrast. Photoelectric effect, no scattered radiation. It's a K-edge effect, results in the emission of characteristic X-ray, and it increases with the cube of the atomic number. So this is why there is so much contrast in diagnostic X-ray at the lower energies. We do not see much photoelectric effect in radiation therapy. In radiation therapy, the effect is mainly Compton effect. This is also called Thomson scattering. It involves much higher energy photons, such as what we see in radiation oncology. It involves the outer shell electrons, and an electron is ejected, ionization takes place. There is scattered radiation, but because the energy of the incident beam is so high, the scatter is always in the forward direction. So it's as if the beam keeps burrowing deeper and deeper into the patient because the very scatter that it releases it in the forward direction. And there's very little side scatter. When we talk about shielding design for radiation vaults, this is important to remember. We're not that concerned with scatter from the patient. We are concerned about stopping the direct beam of the of the linear accelerator, and those are those large direct beam barriers that are usually over 6 feet of concrete. But what is causing most of the secondary radiation in the room is not scatter from the patient, because scatter is in the same direction as the incident X-ray. It's leakage from the target assembly of the head of the machine. The head of the machine is covered with lead internally. If you take the fiberglass off, you'll see a lot of lead. There's only so much lead they can put in there without making the machine too heavy that it will lose isocenter. So there's a trade-off. There's an FDA standard on how much leakage can be present, but the culprit in the room design is not scatter from the patient, but leakage from the head of the machine. Here's an example of Compton interaction. Outer shell electron, ionization takes place, scatter somewhat in the forward direction. Pair production is an interesting effect, and the pair production has a threshold energy of 1.02 MeV. However, it does not predominate in radiation oncology until about 25 MV, and we very rarely see those high energies. So we do get some pair production, but it is not the predominant reaction. So out of the three, Compton, pair production, photoelectric, the one that we use primarily in radiation oncology is the Compton effect. In pair production, an electron-positron pair is created. The electron is quickly absorbed by nearby material. The positive electron, the positron, annihilates rapidly with a nearby electron, causing 2.511 MeV photons traveling in the opposite direction. So it's fun to think about, and this is what physicists do sometimes, you know, as we're sitting around talking about these things. We're actually creating antimatter in patients. Every time we use even a 10 MV beam, we're creating a small amount of antimatter in the patient, and we don't even charge for it. That's a joke. So therapy electron beams lose energy by ionization. Neutrons interact by forming heavy particles, which then cause direct or indirect reactions, and the answer is direct effects, not indirect effects. Direct effects depend upon oxygen, true or false? This is false. The direct effect of ionizing radiation is that it is densely ionizing, bringing about double-stranded DNA breaks. It does not. The direct effect, which is usually with heavy particles or neutrons, does not rely on the oxygen effect. The radiation that we use the most, linear accelerator-based X-ray, relies very heavily on oxygen. Therefore, it is an indirect effect. Does Bremsstrahlung radiation increase or decrease with increasing electron energy? Of course, it increases with energy, and it should always be less than 5% in an electron beam. So in an electron beam, as we'll see later on in this talk, when we talk about the anatomy of a linear accelerator, the electron beam interacts with a scattering foil in the head of the machine to disperse the electron beam. In so doing, it follows the recipe of a high-speed electron hitting a metallic foil. It will give off Bremsstrahlung radiation, but the Food and Drug Administration says it should always be less than 5% of the total energy in an electron beam. So yes, Bremsstrahlung radiation increases with increasing electron energy. So as the linear accelerator goes from 6 to 10 to 15 to 18, yes, the Bremsstrahlung radiation increases in intensity and energy. But if the patient is being treated with pure electrons, the amount of Bremsstrahlung in the beam must be less than 5%. And physicists will measure this when they commission a machine, and it is usually in the order of about 1 to 2% of an electron beam total energy is in the form of Bremsstrahlung, so it easily meets the FDA criteria. And I said I have a note in here, note the implication for total body irradiation, because patient being treated with total body radiation, one has to be very aware of how much Bremsstrahlung radiation there is in that beam of radiation, because it will affect the dose to the bone marrow. The largest contributor to the radiation exposure of the United States population is, and maybe this will come as a surprise to some of you, it is not medical, it is not nuclear, it is not weapons, it's radon. There is about 200 millirem per year that we receive just living in our homes where radon tends to accumulate in the basements. Now, everybody's house is different, depends geographically on where you are, depends on how much rock the house was built on. Radon comes from radium. In New England, we tend to see a lot of granite. Granite traps a lot of radium. There's usually a lot of radon in New England. We all receive about 200 millirem per year from radon exposure. That is the highest contributor to radiation dose to the United States population. We're going to move on to radiation detection instruments, and these are some of the important ones that we use in radiation medicine: diodes, ionization survey meters, Geiger counters, TLDs, and of course the Farmer chamber that physicists use routinely to calibrate the dose in a linear accelerator beam. Here's an example of diodes. Some of you may have seen these as in vivo diodes. They place it on the patient's skin sometimes to measure dose to a pacemaker. And some therapists may have used diodes in this form to do daily constancy monitoring, daily dose monitoring of the linear accelerator as part of their morning warm-up procedure. This is what a diode looks like. It turns out that the area, the sensitive area, is actually a very, very tiny speck centered in the middle of that white ring. So if you take that white ring and you go to the center of that circle, there is a tiny, tiny junction in there. And that junction is 0.1 square millimeters, 0.1 square millimeters. So take that white ring, move it keep it as a circle around there, and find the center of that circle, and that's where the PN junction actually is, that is measuring the radiation. It is extremely, extremely sensitive, small sensitive volume. So that whole diode is really there just to protect that PN junction and to provide some buildup, electronic equilibrium, so it represents a skin dose with all of the buildup and backscatter that goes along with it. Okay, some webinar questions. Can a diode be used to calibrate a Linac? And your choice is A, yes, or B, no. So
all right.
Go ahead. Sorry, Christine.
The poll is live. For those of you who aren't sure whether to click in, you can go to the polls tab and go ahead and answer this question. All right, Frank, I think you can go over the answer.
So the answer to that is no. B is the right answer. You cannot use a diode to calibrate a linear accelerator. Can you use a diode to perform daily morning testing? And your choices are A and B. So go ahead. This is the second question.
Okay, those poll questions are live in the polls section. Okay, Frank, I think you can go over the answer.
And the answer to that one is yes, you can use a diode for morning checks, but you cannot use a diode to actually calibrate a linear accelerator. Here's another question. Which is more accurate, a Geiger counter or a cutie pie? And you can say A for cutie pie or B for Geiger counter. Which is more accurate, a cutie pie or a Geiger counter, A or B?
Okay, Frank.
Okay, and the answer is Cutie pie. So I guess the next question is, what's a cutie pie? And there it is. You've all seen one of these. You've seen your physicist running around with this survey meter from time to time. This is a cutie pie. That's what a cutie pie is called. It's an ionization survey meter, way more accurate than a Geiger counter. Geiger counters are used to quickly find radioactive contamination, such as when you drop an iodine seed in the operating room during a prostate implant. You would use a Geiger counter to find it. Geiger counter is extremely sensitive, notoriously bad accuracy. The cutie pie, however, just the opposite. Not very sensitive. You wouldn't use this to find a seed on the floor because it takes a little while to get a reading on it. However, it is way more accurate, and you would use this if you were evaluating the concrete shielding of a linear accelerator vault. You would turn the machine on, irradiate a big water tank, a Phantom, and walk around the room with this cutie pie, measuring the radiation dose with a very high degree of accuracy to see if the shielding design was adequate for that room. Now, cutie pie, you're probably wondering, where the heck did he get that? That is a holdover term from the Manhattan Project. So a little bit of history here. During the development of the atomic bomb in the United States in the 40s, everything was top secret, and everything had a code name. And the code name for this instrument, which was developed as part of the safety program around the nuclear program and at Los Alamos, was cutie pie. So this is a holdover from the old atomic age, where everything had a code name, top secret. So here is the top secret cutie pie. Now this is interesting. So here's a cutie pie, and this is an experiment that I did, and this is going to lead into some of the other things that we're going to talk about later on in this presentation. But that is not a fluke. And one of the things I want to just kind of maybe whet your appetite over here a little bit, get you kind of excited about where is he going with this. You can see the collimator of the linear accelerator, and I actually turned the machine on, ran it for about 10 minutes at a high energy, and shut it off, of course, and entered the room and propped up this cutie pie facing right into the collimator of the linear accelerator. The beam is off, the machine is off, everything is shut down, and I'm getting 3.5 MR per hour. This is a real reading, 3.5 MR per hour. So I'm going to keep you hanging on this. Where the heck is that coming from? If the machine is shut off, how can you possibly be getting 3.5 MR per hour? And we are going to talk about that. Let's go back to the Geiger counter. Geiger counter operates by a total avalanche effect. One photon comes into the Geiger tube. The Geiger tube is gas under pressure. And because there's so much pressure within that tube, and the voltage is so high, up to 900, 1,000 volts in a Geiger tube, that one photon causes an ionizing event that creates a whole avalanche of events, and you get this big spike of a reading. So the Geiger counter is constantly turning on, turning off, turning on, turning off at a very rapid rate, and is exquisitely sensitive to even one photon. And yes, you can take a Geiger counter outside and measure background radiation from the sun or from the earth. A Geiger counter will easily measure background radiation because of its sensitivity. Not terribly accurate, but exquisitely sensitive for finding small amounts of radiation or a lost seed on the floor of the operating room. Here's an example of a Geiger counter. Here's one that is used quite often in the operating room. It's called a pancake probe, so it can scan that whole area in that handheld probe, and you can quickly scan the floor or the bench or work area to find contamination. Now here is the world famous 0.6 cc Farmer chamber. This chamber is used by physicists everywhere to actually calibrate the linear accelerator beam. That is a tank of water in the background. This is a water phantom. Physicists use it all the time to accurately calibrate the output of a linear accelerator. The chamber is waterproofed, and as you see, Okay, let's go back to that. The chamber is waterproof. I have another slide that shows it waterproof in water. It's submerged in water, and dose is measured by that Farmer chamber. And this is how it's done. So let's talk about how radiation is measured and the effect of temperature and pressure on those readings. First of all, the unit of gray. I have searched far and wide, and I have come up with, finally, who the gray was named after. I'm sure you've all been wondering about this in your training. Who the heck is this gray guy? Well, here he is. His name is Louis Gray. He died in 1965, and he was honored. He was, of course, a radiation worker, a radiation researcher. There he is, Louis Gray, and the gray is named after him. It equals 100 rads. So there he is, Louis Gray. Now recall, photon interactions with matter. The basis for dose is the kerma, kinetic energy released in matter. Remember this slide from a little while ago. Kinetic energy released in matter, the kerma. How do you get dose? How do you calibrate a linear accelerator if you've got this Farmer chamber in a tank of water? Let's see if I have a picture of this. There it is right there. Okay. See the Farmer chamber? It's submerged in water. So it's waterproofed. There's the linear accelerator beaming down on it with a 10 by 10 field. There's the Farmer chamber in water, and I want to calibrate that linear accelerator. So let's go back. Dose from exposure. So in the thimble part of that chamber, remember there was this black thimble at the end. There is ordinary room air in that thimble. Ordinary room air. That thimble communicates with the air in the room. Whatever the temperature and pressure is in the room, the same temperature and pressure result is residing in that black thimble, that little end of the chamber, 0.6 cc's. Ionization releases kinetic energy, ionized electrons, in that air. So we're collecting, we're actually measuring ionizations produced in a thimble of air. But air is not tissue. But if we measure the energy released in joules per kilogram of air, we have dose to air, and then we can mathematically massage that dose to air to get dose to the surrounding water. So there's a lot of mathematics involved here, but what we're really doing when physicists calibrate a beam of radiation, they actually look at the dose to that small thimble of air in the Farmer chamber and then mathematically adjust it to the water that surrounds it by something called stopping power ratios. So this is the field of radiation dosimetry. So thimble, Farmer chamber, bubble of air at room temperature and pressure. Radiation releases kerma in the thimble. That gives us dose to air. We use stopping power ratios to mathematically correct that, and we find dose to water. If we find dose to water, we also know dose to fat, glandular tissue, muscle tissue, bone tissue. If you know dose to water, you can easily get dose to the other tissues that make up the human body. Most of the human body is water. It's a natural to measure in water, mathematically adjust them by really no more than a few percent, because we rely on the Compton effect, and the Compton effect does not rely on the cube of the atomic number the way the photoelectric effect did. The Compton effect was more related just to electron densities, which don't vary very much between the human tissues. So radiation dose to water is essentially dose to fat, gland, muscle, and bone within a few percent. And you're probably asking, well, how do we correct for that few percent? And the answer is very easy. Because every patient gets a CAT scan as part of their treatment planning, the CAT scan has Hounsfield units. The Hounsfield units relate to tissue density. The treatment planning computer can very easily correct for the tissue density of fat, water, muscle, gland, bone, etc. So those few percent are corrected for in the treatment planning system using the Hounsfield units from the CT simulation. So not only does the CT simulation give us the patient anatomy to work with, but it also gives us the tissue densities that the treatment planning computer must use to accurately determine dose to the patient. Those are your heterogeneity corrections. That's how you apply heterogeneity corrections to a planning system. Okay, Systeme Internationale. 1 sievert is 100 rem. A millisievert is 100 millirem. 1 gray, this is the important one. 1 gray is 1 joule per kilogram. So there was a push, many years ago to get away from rads. They didn't like the rad being 100 ergs per gram. They didn't like this. They said, we got to get on the MKS system. So a joule per kilogram is now a gray, and a gray equals 800 rads. So 1 joule per kilogram is the official radiation absorbed dose. Here's the setup for measuring absorbed dose. Farmer chamber, black thimble with air. Chamber communicates with the outside atmosphere through a small vent in the back of the wire, and radiation dose to the air gets converted mathematically to dose to water. Dose to water gets converted by the treatment planning system to dose to all of the tissues that make up the patient. Calibration protocols. The accepted protocol today is called TG51. It stands for Task Group 51. Now, task group of whom? Task group of the American Association of Physicists in Medicine. That's the professional organization that physicists belong to, the AAPM. The AAPM produces a prodigious amount of literature on how to do things. And one of the task groups came out with this report, TG51, that is the cookbook on how to calibrate a linear accelerator. So the accepted protocol is TG51. It very, very clearly tells a physicist how to measure dose in water. TG51 is the protocol. Now, can you measure dose in plastic? Like, many, many years ago before TG51, physicists could be measuring in plastic, Lexan, lucite, polystyrene. I've heard of all different things that people were measuring dose in, but TG51 eliminated all of that and said, you know what, water is the same no matter where you go. We are going to standardize our protocol to dose in water, knowing full well that once you got dose to water, you can, through CT number, Hounsfield unit corrections, you can get dose to fat, dose to gland, dose to muscle, dose to bone. So once you know dose to water, you know dose to everywhere in the patient. Question comes up a lot of times, is a Rankine exactly equal to a rad? It's not. It's almost equal to a rad. A Rankine in air, which is the amount of ionization produced. It's a fixed amount of ionization produced in air. Definition of a Rankine results in exactly 0.869 rads in air. So there is a factor that is used for tissue conversion from air to tissue. Take that 0.869, multiply it by the F factor, and it converts dose in air, which I said we get in the pharma chamber, to dose in tissue. So basically, a lot of mathematical manipulation, all very nicely laid out in the TG51 protocol. One of the things physicists have to be very concerned about is temperature pressure in the room, because the thimble in the pharma chamber contains room air, as I said. Room air varies depending upon temperature and pressure. You could have fewer molecules of air. You could have more molecules of air. Depends on the pressure, depends on the temperature. So therefore, when you see physicists working with pharma chambers, you will always see a thermometer and a barometer nearby, because the reading must be corrected for temperature and pressure at the time of measurements. So how do you know really what the final absolute number has to be? Well, it turns out, we send that chamber to a standardization laboratory. The standardization laboratory gives us a calibration factor based upon something called STP, standard temperature and pressure. So the chamber has a calibration number at exactly 22 degrees centigrade, 760 millimeters of mercury. So that is the exact calibration. If the temperature in your room or the pressure in your room isn't exactly 22 degrees C, 760 torr, then you correct it mathematically. That's why when you see a pharma chamber, you will usually see a thermometer and a barometer nearby to make the necessary corrections. Okay, back to that cutie pie and neutrons. Neutrons were the cause of that cutie pie coming up with 3.5 MR per hour. Neutrons are a problem when you get above 10 MV. There are actually neutrons at 6 MV, but very, very few. We don't start to worry about neutron contamination until 10 MV. So I have a lot more to say about neutrons in some of the upcoming slides. Neutrons have a higher quality factor. They're going to give unwanted dose to patient and staff. Neutrons make things radioactive. It's a fact. I mean, that's how things become radioactive. A nucleopile is a supply of neutrons. If you put in stable cobalt-59 into a nucleopile and take it out 2 years later, you have highly radioactive cobalt-60. Neutrons make things radioactive. Neutrons require very expensive shielding. It's called borated polyethylene. Boron. Boron has an affinity for neutrons. When you're shielding a room for neutrons, you have to incorporate boron and polyethylene. It gets very, very expensive. You need special equipment to detect neutrons. FYI, a thermal neutron is 0.025 eV. I doubt if you'll ever be asked that on an exam, but that's the definition of a thermal neutron. And energies above 10 MV, we start to worry about neutrons, and we need to build that consideration into our room shielding. Okay, so here we go, back to the collimator example. Now, run the beam at 10x. Here is a handheld Geiger counter. That's what this is. This is a handheld Geiger counter. This is an experiment. These are pictures of an experiment that I did. So, ran the machine for just a little while. 10 MV. Go in the room at time 0, 144 micro R per hour. Wait 5 minutes, 46.7. Same place against the collimator, 46.7. Wait 10 minutes, 28.4. What's going on here? Rapid decay. So whatever the neutron is making radioactive in the head of the machine is rapidly decaying. And probably by the end of a half an hour, 15 minutes, half an hour, there will be hardly anything left. So the bad news is that at 10 MV, we start to get neutrons, and it makes things radioactive, including the head of the machine. The good news is that whatever's being created doesn't hang around for very long, a very, very short half-life. I'm going to say a little bit more about this because it really is a fascinating story, and it has to do with your radiation badge reports, too. We're going to tie this all into your radiation badge reports in a moment. At 15 MV, notice it jumped way up. So 15 MV, definitely neutron contamination in the target, in the collimator, in the flattening filter. Neutron contamination made things radioactive in the head of the machine. And we get a much higher reading at 15x, as you would expect. Now, quality factors play into this again, because the quality factor for X-ray and gamma ray is 1. For neutrons, it's 10, and for heavy particles, it's 20. And look at the size of that door. This is called a direct shielded vault. So this vault does not have a maze. You can actually see the treatment couch in the background there. This door takes the place of the concrete wall, and within this door is lead and borated polyethylene. So you need the borated polyethylene to take the place of concrete. Concrete is a very good absorber of neutrons. Neutrons don't get through the concrete that shields a regular vault, but neutrons can get through a leaded door very easily. Lead does not stop neutrons. Hydrogen material does. Used motor oil will stop neutrons. Butter will stop neutrons. Crisco will stop neutrons. Okay, you need a lot of hydrogen. Fat will stop neutrons. Neutrons require lots of hydrogen. So borated polyethylene has the hydrogenated polyethylene, and boron, which has definitely a high affinity for neutrons. So this door has lead and borated polyethylene in it to keep the staff safe on the outside. This is called a direct shielded vault. You're seeing more and more of these today as architects don't want to give up space to a maze. They're using these composite doors, which weigh about 35 ton. They're heavy, and they're on a rail system. 35 ton on these doors. So what material would you use to reduce neutrons? And the answer is, of course, borated polyethylene or other high hydrogen materials. This is a special meter for neutrons. You need a neutron moderator to be able to measure neutrons, so it requires special instruments. Here's what happens when neutrons hit concrete. Remember, neutrons make things radioactive. Let's play that back again. Here comes the neutron. Bang, 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 bang. Slams into the concrete. The concrete actually emits gamma radiation. The neutrons have made material within the concrete slightly radioactive. So you're wearing a badge. Radiation safety officer has the badge records. How long does the radiation safety officer have to keep, by law, radiation monitoring records? This is a webinar question.
All right. Looks like some folks already clued in to the new poll that is up. You can go ahead and answer that. We'll give you a few moments to check out those different options.
So, forever, 5 years, or 3 years?
All right, looks like everyone's had a chance and some interesting results.
Okay, the answer is forever. Radiation records are forever. And it's interesting, if a department closes its doors and everybody scatters, most of the states require that those records be remanded back to the state. You cannot get rid of radiation records. Radiation records are forever. Because there may always be a need to find out how much radiation the worker had at some point. So you cannot, and it's actually a lot easier today. Back in the day of paper records, things did get lost. But the monitoring companies today have everything computerized, and you can go back and pretty much find anybody's record over the last 10 or 15 years. Now, here's this interesting stuff that I was alluding to. Here's a badge report from a radiation department. And this is very, very typical. You'll notice below the bottom red circle, there's this thing that says 1 rem. It means that the Luxel badge, the badges we use today, are sensitive all the way down to 1 millirem. I meant millirem, MR, millirem. And workers occasionally get M, which means too small to be measured, which means below 1 millirem, or some of the single digit numbers that you see there. You see 8s and 3s, and sometimes 4s and 5s and 6. And it's not unusual today to find single digit numbers on a radiation badge report. What is going on here? Well, these are our OSL, optically stimulated luminescent monitors. OSL stands for optically stimulated luminescence. This is like the older thermoluminescent dosimeters that we wore on our fingers for finger badges, or we may have used TLD, thermoluminescent dosimetry, on patients for in vivo monitoring. The new badge over the last, less than 10 years, optically stimulated luminescence. So it takes the place of the thermal part and actually uses a laser to get these things to read. So these are semiconductors. They're crystals. They record. Internally, the crystal structure changes. The chemistry of it changes, and radiation that is absorbed by this crystal can be read out at a later time by measuring the amount of light that the crystal gives off when it's hit with a laser beam. This is what they look like. That wafer is a wafer of lithium or lithium fluoride or calcium fluoride. Now, real interesting is the sandwich that holds it together. The sandwich, if you ever crack one of these things open, the sandwich that holds that crystal, your badge, really has different filters in it. You see the filters in it? There's an open area, there's a lead filter, there's an aluminum filter, there's a copper mesh. So what happens is that the radiation impinging on this badge, impinging on the wearer, will set up in these 4 quadrants different chemical reactions within the crystal. The laser hits it and reads the amount of light coming off of the 4 quadrants, calculates that, converts that to a dose. But because the radiation passed through a filter sandwich, the amount the crystal is recording is actually dependent upon the energy of the radiation. The computer can tell, based on the relative readings throughout that badge, exactly what the energy was and assign the right correction factor. So these badges are exquisitely accurate today, accurate down to 1 millirem. And this is a really, really good dosimeter, OSL, optically stimulated luminescent. That's what the inside of your badge looks like. And it will very accurately tell you what your radiation dose is. There's the numbers. So what is the sensitivity of optically stimulated luminescent badges? Usually down to 1 millirem. Would a OSL badge that we all wear at work, would it record neutron dose? The answer is no. You need a special neutron monitor for that. Let's talk a little bit more about neutron production. You're going to see this slide again, maybe tomorrow, I think, when we talk about how a machine works. But here's something called the beam path, the beam optic of a typical linear accelerator. There is a grid on the left, which emits a cathode grid, which emits electrons. The electrons get accelerated through that 4-foot-long accelerator. They then enter into the bending magnet, 270 degree, hit the target, produce Bremsstrahlung radiation, flattening filter, ion chamber, beam optics. Okay, what's going on here? Remember, beam optics. Okay, what's going on? Let's follow the path of the electron. Okay, so, Okay, here's the electron in blue. The electron hits, the electron is the dotted line, dot, 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 bang. The electron hits the target, gives off high energy Bremsstrahlung radiation. Okay, so far so good. The high energy Bremsstrahlung radiation is such a high energy that it interacts with the target, with the material that the target is made of itself, and anything that's surrounding the target, like a primary collimator, and something called photofission happens. These high energy rays are able to knock neutrons out of the material that makes up the target, the primary collimator, the flattening filter. And the neutrons, as we said, go on to be captured and make things radioactive. The lead, the tungsten, the aluminum, any of the metals, the copper, anything within the head of the machine can be activated by neutron capture. It's the same way a nuclear pile works. Like I said with cobalt-59, keep it cobalt-59 in there long enough, it becomes cobalt-60. Neutrons make things radioactive. That radioactive material gives off a gamma decay. But wait, there's more. After the neutron undergoes neutron capture, there's also the release of fission material. The fission material can go on and cause a gamma release, which will then go on and cause a pair production. So there is a lot of contamination going on in the target assembly, the head assembly of a linear accelerator. So yes, we're very concerned about neutrons, and we have to protect against them with borated polyethylene. The higher the energy, the more neutrons. So you see 6 and 10 MV, which we mainly use today because of VMAT and IMRT, very, very nicely keeps the neutron contamination level down low. And another reason why 15 MV and 18 MV not recommended with IMRT, because of the neutrons associated with the higher multi-units. Here's a webinar question. How much is the typical workload for a Linac increased by IMRT? And here are your answers. Here are your choices. Typical workload. So by typical workload, I mean if you look at a non-IMRT department and said let's look at a non-IMRT department and say there's 50,000 centigrade per week at the ISO center for my average patient load in a non-IMRT department, 50,000 centigrade per week. That's called the workload. If you're doing a shielding design and you have to take into account total amount of radiation in the room, you have to bump it up for IMRT, because we know that IMRT treatments take longer than regular treatments. So how much does a physicist doing a shielding design bump up the workload because of IMRT? So your choices are, is it 2 times the workload? Is it 3 to 4 times the workload? Is it 10 times the workload? When we do a shielding design for head leakage and neutron contamination, especially if the department is doing a lot of IMRT, we have to bump up the workload to account for the higher number of monitor units. How much is the bump up due to IMRT? Webinar question.
Okay, so go ahead and answer that in the poll. Looks like most people have had a chance to weigh in, so I think we can go over the response. Frank?
And the answer is B, 3 to 4 times. 2 times, not quite enough. 3 to 4 times gives you plenty of conservativeness in your calculations. 10 times is way too much. So the answer is IMRT has caused a 3 to 4 times bump up in the workload for shielding design. Now you know that there are different collimator delivery systems. There's something called sliding window. There's the step and shoot, which was how we all started doing IMRT. And today we have VMAT, volumetric modulated arc therapy, volumetric modulated arc therapy, VMAT. And the advantage of VMAT is that it really lessens the amount of MU. It is a very efficient beam. So when you stop to look at an analysis of monitor units delivered, let's say for lung, prostate, head and neck, you find that the VMAT monitor units are always less than the step and shoot monitor units. So many departments have embraced volumetric modulated arc therapy. Electa calls it VMAT. Variant calls it rapid arc. But there is definitely a savings in monitor unit, which means a couple of really good things. It means that there is less background radiation to the patient in the room, but it also means that the treatment times are shorter and less of a probability for patient motion. So this is where I planned on having the break. I did finish a little bit early. I finished about 10 minutes earlier than I had intended to. But this is a good place to stop and call it a day on the first half of this. And tomorrow, when we rejoin at 6 o'clock tomorrow Eastern, we will talk more about radiation protection and quality assurance. So Christina, I'm going to hand it back to you.
Okay, thanks, Frank. So we have a couple of comments and a question that I'd like to just take a moment if we could go over. The most recent one here, according to 10 CFE 36.81, dosimetry records are only retained until a license is terminated. Do you have a response for that?
Yeah. Now, 10 CFE or 10 Code of Federal Regulations, that's the Nuclear Regulatory Commission. I mean, that's all well and good, but a lot of times the state has a say in this, and the state may want you, the licensee, to turn those records over. So the best thing is to just keep them forever. So if a license is terminated, and you have all of these radiation records, the best thing to do is to turn them back over to the state and see what they want to do with them.
Okay, thanks for answering that one. And then we have another comment, which I believe is an answer to a question. So Bremsstrahlung is for electrons, Compton is for photons, and I believe that was a comment in relationship to this question. I thought Bremsstrahlung is the most common interaction, not Compton.
Okay, two different things. Bremsstrahlung, and I'm sorry if I didn't quite explain it the right way. Let's start with Bremsstrahlung. Bremsstrahlung is German for breaking radiation, which means that you break, you stop the momentum of the incident electron. Now, when I say incident electron, and I don't think I was clear enough on this, so I am sorry for that. The incident electron is the electron that's being accelerated in a linear accelerator. So the electron accelerated in a linear accelerator slams into a tungsten target in the linear accelerator, producing Bremsstrahlung radiation that we use on patients. So yes, we are always using Bremsstrahlung radiation on patients. Now, when that radiation interacts with the patient, it then has a choice based on its energy of either photoelectric, Compton, or pair production. So let's go back again. The gun of the machine, the filament, produces electrons. The electrons get accelerated through the accelerator. They slam into the tungsten target in the head of the linear accelerator. Bremsstrahlung is beamed down on the patient. We treat patients with Bremsstrahlung radiation. When that Bremsstrahlung enters the patient, depending on its energy, if it's low, it'll undergo photoelectric. If it's medium-high, which is what we use in therapy, it'll undergo Compton. If it's high and above, it will undergo pair production. I hope that explained it a little bit better.
Okay, thank you. And our last question here. What are the pros and cons for a female worker to declaring a pregnancy to the RSO?
I think it should always be done to have it in writing. And the radiation safety officer with the department manager will make sure that the pregnant worker does not get more than 500 millirem during the period of gestation. We're going to talk more about this tomorrow when we talk about the radiation protection guidelines. But just to answer the questioner's comment here, when physicists do a radiation shielding design for a linear accelerator vault, they can use two numbers. The first number is for a controlled area. And all of the guidelines today say when you design for a controlled area where the therapists actually run the machine, that should be designed for 500 millirem and less. The area occupied outside the room by the general public, such as an office, a waiting room, a corridor, the outside areas get designed for 100 millirem per year. So 500 millirem per year for control areas, 100 millirem for outside. So it's always a good idea to declare pregnancy. This way, management and the RSO can look at the individual situation and say, hopefully, that you have nothing to worry about because this area has been designed for under 500 millirem. In fact, look at the badge reports. And we have workers here that have been badged for all these years, and their reports show maybe 10 millirem over 3 months. Multiply that by 4, so maybe 40 millirem a year. You're allowed 500. Most of your coworkers are getting 40 and under. It is a safe environment. Don't worry. Keep working there. So it always is a good idea to declare the pregnancy, make it official, and then that triggers a review by the radiation safety officer. In radiation therapy, we all tend to use one badge, and we wear that badge on our lab coats, or we wear it at the waist level. If it was a diagnostic department, however, very, very different, because in diagnostic x-ray, they wear lead aprons. The rule for a lead apron is you wear the badge outside the apron, so it tells you what your face is getting, and your thyroid if you're not wearing a thyroid shield. So in a diagnostic department, you wear the badge outside your apron. Now that may give a falsely high reading to what the fetus is receiving. So in a diagnostic department, usually the pregnant worker will be issued a second badge to put waist level below the apron, inside the apron, to monitor fetal dose.
Okay, great.
Yep.
So we have just one last question that popped
Sure.
in here at the last minute. Can you explain QF neutron continuous with energies? Why?
QF, so quality factor with neutrons, and depending upon the energy of the neutron, the quality factor may change. So quality factor, very, very dependent upon something called linear energy transfer. Now, I didn't want to get too deeply into the physics behind it, but linear energy transfer refers to how much energy is being transferred per micron of tissue. If a particle, depending upon its energy, has a very, very high linear energy transfer, it is effectively causing double-stranded DNA breaks. It is like a Mack truck entering tissue and busts everything apart with a very high killing potential. So depending upon the energy of the particle, and neutrons can have different energies, just like protons can have different energies, depending upon the energy of the particle and its linear energy transfer, the quality factor, which is a measure of biologically how damaging is this radiation compared to regular, ordinary 200 kV X-ray. How damaging is this radiation? Well, particle radiation has such lethality because it is causing double-stranded DNA breaks with no chance of repair. So the quality factor goes up, and rad for rad, dose for dose, these high LET particles are very, very lethal and cause a lot of damage. Whereas the radiation that we give patients, the X-rays that we're giving patients today, have a relatively low linear energy transfer, and it requires several hits, called target theory. Several hits within the nucleus of the cell have to be rendered dead before the cell is actually dead. So sparsely ionizing radiation with low LET can have a very low quality factor, requiring more rad dose. High LET radiation requires less of a rad dose for the same amount of killing because it is an extremely efficient particle means of killing off DNA. I hope that answered the question.
All right. Well, thanks again. And thank you for presenting this webinar, Frank, and to all of you for joining us for this free event hosted by WePast. This and other recorded webinars will be available to WePast subscribers, and you can register through wepast.com to become a subscriber. For up-to-date information about upcoming webinars, be sure to follow WePast on Facebook, Twitter, and Google+. And thank you, Frank, for presenting this webinar.
Thank you all, and we'll see you tomorrow.
Have a good night.